This problem says a projectile of mass 2 kg is fired in air at an angle of 40 degrees to the horizon at a speed of 50 meters per second. At the highest point in its flight, the projectile breaks into three parts of mass 1 kg, 0.7 kg, and 0.3 kgs. The 1 kg part falls straight down after breakup with an initial speed of 10 meters per second. The 0.7 kg part moves in the original forward direction, and the 3.3 kg mass goes straight up. At the peak of the peak after explosion, so this is at launch. Find the speed of the 0.3 kg and 0.7 kg piece immediately after breakup. How high from the breakup point does the 0.3 kg piece go up before coming to rest? Where does the 0.7 kg piece land relative to where it was fired from? Okay, so there's this problem combines quite a few things. All right, so here's what's happening. So let me, you launch something, and what is the trajectory of this thing?
40 degrees to the right.
It's a parabolic trajectory, and when it gets to the top, is it at rest? No. So its x component of its velocity does not change, and so it'll have an x component of velocity. The y component of velocity has gone to 0. So right before the explosion, here's the initial momentum. And it explodes. Now it could explode into a million pieces. The momentum of all those pieces should equal the momentum just before it explodes. Okay? So, and all the momentum will be in the x direction. So this happens to explode into three pieces, one piece going straight up, one going straight down. So those momenta should cancel. And one piece going in the x direction. So that piece that's going in the x direction should have all the momenta that it had before. And these two momenta should cancel. Okay, so that's all right. So what we'll do is I'll just go on making parts to the problem. I'll break up the problem into parts. So launch speed is, the mass is 2 kgs. This at 50 meters per second. 40 degrees. Okay. So initial velocity is 50 cosine 40 I plus 50 sine 40 j, and this is equal to okay, so what is the velocity of the object just before exploding? The velocity is 38.3 I plus 0 j. Okay, everybody understand that?
No.
All right. What part do you not understand?
The J.
So that's what we were talking about. When it's rising, what is happening is the y component of the velocity is going to 0. That's what's going to 0. The,
While X continues, Y starts to slow down.
right. Right. And why is the x component not changing and the y, only the y component changing?
Still moving.
Very good. here's what our friend said. The acceleration due to gravity is there. Acceleration is 0I minus GJ. Okay, so this is what is telling you that the x component of the velocity is not changing. Only the y component of the velocity changes. You have acceleration in the y direction. Okay? All right, so now let's do part 2 of the problem. So you have the explosion, and momentum after the explosion should equal momentum before the explosion. Okay? And now, since we're dealing with two-dimensional vectors, final y component should equal initial y component. Final x component should equal initial x component. Okay. So, what is the initial x component, y component of the momentum? Initial mass times, and this is 0. So just before the explosion, remember, initial velocity was, I'm going to rewrite it, 38.3 I plus 0j. So this guy is 0. Okay? You guys understand? What is the initial x component of the velocity? X component of momentum? Mass times v, 2 kgs times 38.3 minutes. Okay? V, momentum is mass times velocity, y component of the velocity. And there's y component of the velocity, which is 0. All right, so now let's look at, so after the explosion, okay, so the explosion has happened over here. And after the explosion, you have 3 pieces. Here's a 0.7 kg piece going in that direction. We'll call it V.7. And so it breaks up into 3 points, 1 kg, 0.7, and 0.3. The 1 kg falls straight down. Okay, and the 0.3 kg piece goes straight up. So this is going at 10 meters per second, and that's 1 kg, and this is going straight up, 0.3 kg. Okay, so this is after the explosion, and all right, now let's do some calculations. So since these guys have no x component of velocity, this guy's x component of this guy's momentum should equal that. Okay? Only this guy has x component of momentum. These guys have no x component of momentum. Okay. So Pix should equal P final x, and that's 76.6 should equal 0.7 kg times the velocity of the 0.7 kg object. So that piece is going at 107 meters per second. Okay. And so let me point out something. When this piece got to the top and exploded, just before the explosion, it was going at 38 meters per second. And it was a 2 kg object. Momentum is mass times velocity. So if your mass decreased by a factor of 3, your velocity should increase by a factor of 3. Okay, so a 2 kg object in that direction became a 0.7 kg object. The rest of the mass was shot out in the y direction. So that's why its velocity was 3 times as great in the x direction. Okay. All right, let's look at the y component of the velocity. P initial y equal to 0 should equal P final y. Okay. So 0 should equal 0.3 kg times V.3 plus 1 kg shot down at minus 10 meters per second. It was going downwards and our axis, y-axis is pointing up. Okay. So the velocity of the 0.3 kg object is 10 divided by 0.3, which is 33.3 meters per second. All right. So now we have the velocities of the 3 objects after they exploded. Okay, I'll draw another diagram, but so here's what we have found. You shot a shell at the bottom, 40 degrees at 50 meters per second. It goes on a parabolic trajectory. Just before it explodes, its velocity is and then, well, okay, and this is going at 109.4 meters per second. This was going at 10 meters per second, and this piece was going at 33.3 meters per second. This is 0.3 kgs. Oops. I'm trying to write as little as possible. I don't want the diagram to get messy. This is 1 kg, and this is 0.7 kg. Okay. And okay, I'll write this velocity. That velocity is that velocity is 38.3 I plus 0j. Okay, so what we are saying is just before the shell exploded, it's going at 38.3 meters per second. It's exploded into 3 pieces. One piece is going at 109 meters per second. This piece is going at 33 meters per second. This piece is going at 10 meters per second. Okay. All right, so that's what we have found so far. And now, okay, so we have found that find the speed of the 0.3 kg and 0.7 kg pieces immediately after breakup. That was part A. So now part B. How high will the breakup from the breakup point does the 0.3 kg piece go before coming to rest? Okay, now, so part B, the question is, now how high will it rise from here? Okay. All right, so, and for that, all right, so here's the 0.3 kg piece. It's going at 33.3 meters per second. And there's one of several ways you can solve this. Okay, we'll use this equation. V final square is equal to V initial square plus 2A Y final minus Y initial. Okay, so this is 0. This is 33.3 meters per second plus 2 times negative 9.8 meters per second square. And this is the height above which it rises, above the explosion point. Okay. And you can solve for h. This works out too. .6 meters. So what we just solved for is this piece will rise 56 meters above the explosion point. Okay.
I have a question on just this equation. I know we use this one in a different chapter. My only question is with A, we use G. So is A just, when we're applying this equation, is A just a constant force that's being applied to the object that we're trying to find the final velocity of?
Okay, what this equation is telling you is what is the final velocity of the object that is accelerating in with that acceleration. This is we're looking at it in one dimension. This is the dimension we're looking at. So it was going with this initial velocity, and there's the final velocity. The acceleration of this object was the acceleration due to gravity, which was in this direction.
Okay. Thank you.
So U equals Y final minus Y initial.
I'm sorry?
U equals Y final minus Y initial.
That's V. V final square is equal to V initial square plus 2 times A times the displacement.
Okay, I'm saying so displacement equals V.
That's H, the height. Doesn't matter what it's called. But. All right, you guys understanding what's going on? All right. There's more to it. Since you guys are enjoying it, it keeps giving. Where does the 0.7 kg piece land relative to where it was fired from? Okay, so now here's where he fired it from. This guy took off, and so he'll still go on a parabolic trajectory, except that those two parabolas are different. Okay. This is part C. Okay, so let's make sure we understand the diagram. Okay. And then the second parabola is wider because It's moving faster. Okay, so this object is going at 109.4 meters per second. We'll need to find this height and so on. Okay, so we'll call this R1 and this R2. That is the question. Okay. All right, there was a whole bunch of information we need to, so all right, V naught is 38 point, so the initial velocity is 38.3 I plus, there it is, 32.1 J. Okay, so let's find how high the object rises before exploding. You will need that height because the higher it rises, the longer the time of flight and the further it will go. Okay, so you'll need this height for the time of flight. Okay. Now, you can get the time of flight, well, actually, you will not need to calculate this. Okay, so I'm going to say this. The time of flight, the time it takes for this guy to get to the top, is equal to the time it takes for this guy to fall down. Did you guys understand that? Okay, the time it takes for this guy to get up there is how long it takes for his y component of the velocity to come to 0. Okay? All right, so we'll say this t and this t. Okay. So note the black t is equal to the red t. Okay. Everybody understand that? The black t is the time it took for it to go up, and the red t is the time it took for the guy to come down. Okay. So the color coding is also a variable. Okay. All right, let's calculate the black t. Okay, so that's how long it takes the guy to get up there. .28 seconds. So the time of flight is 3.28 seconds. So R1 is V initial x times t, which is 38.3 meters per second times 3.28 seconds. Okay, so what we did there was, here was the x component of the velocity. So the x distance traveled was the x component of the velocity times the time of flight. That's the x distance traveled. For this guy, it'll be the x component of the velocity, which is 109.4 meters per second, times the time of flight. But this time of flight is the same as this time of flight. Okay? So we will do R2 is, we'll call it Vx times that, V final x, 109.4 meters per second times 3.28 seconds. Okay. So the total distance traveled half a kilometer away. And half a kilometer is roughly from here to Nova Road. Okay. So that's how far the shell would fall. All right. I'm sure you guys have questions on that, but we'll make Ben earn his living.